Welcome to The Explainer. Today we're diving into an absolute paradigm shift in hardware. We're looking at something that could legitimately solve artificial intelligence's rapidly escalating energy crisis. We are going to explore a blueprint for something fundamentally new, and that is continuous variable thermodynamic computing.
So, we have to start with a pretty profound question. For decades now, our digital systems have expended massive, almost unimaginable amounts of energy just trying to eliminate natural thermal fluctuations. Think about it. We cool our data centers to the extreme, we build complex error-correcting codes, all just to keep the physics of the real world at bay. But what if we stopped fighting nature and actually started using it? To really grasp why this matters, we need to look at the theoretical floor of energy consumption for computation. It's known as the Landauer limit, and it sits at roughly 0.7 times Boltzmann's constant times temperature. Now, modern AI algorithms rely heavily on probability and randomness, right? Think of the noisy gradients, or the massive sampling happening in large machine learning models. Trying to force our rigid, deterministic digital hardware to simulate this natural randomness is incredibly inefficient. We are literally burning megawatts of power to simulate something the universe just does naturally. This massive inefficiency is exactly what's pushing us to seek out new operations that get us much closer to that absolute minimal energy limit.
Okay, here's our roadmap for today. 1. AI's energy bottleneck. 2. Embracing nature's noise. 3. Energy-based models. 4. Thermodynamic neurons. And finally, number 5, the future of computing.
Let's kick things off with Section 1, AI's energy bottleneck and the true cost of fighting noise.
The computing paradigms we are most familiar with today, both classical, digital computers, and even emerging quantum computers, are basically at war with thermodynamics. Classical computers need to constantly pump out heat to prevent thermal fluctuations from flipping a bit and completely ruining the binary logic. On the other hand, quantum computers require extreme refrigeration and massive radiation shields, because even the slightest bit of thermal noise causes quantum decoherence. But thermodynamic computing takes the exact opposite approach. It treats that exact same thermal noise not as a bug that needs to be squashed, but as a core computing resource.
Moving into Section 2, embracing nature's noise, surfing the river.
All right, let's dive into the physics here. The answer to this energy problem lies in what's called underdamped Lagrangian dynamics. This is a physics concept that describes how a system driven by inertia and heavily influenced by random thermal fluctuations and damping will naturally settle into low-energy states. So instead of calculating probabilities line by line in code, which is what we do now, an engineered physical system undergoing Lagrangian dynamics basically does all the heavy lifting of probabilistic sampling for us, just by existing in its energy landscape. It's like letting a ball naturally roll down a hill into a valley instead of calculating every single micro-movement of its descent.
This visualization right here brilliantly illustrates exactly how we manipulate that landscape. We are looking at a double well potential. Let's break this down thoroughly, because this is really the core computational primitive. Up on the top left, you see these energy curves where the bias or tilt is at 0. As we increase a parameter they call lambda1, you can see the curve morphs from a single wide bowl into 2 distinct dips, creating a double well. Now look over at the probability distribution on the top right. Notice how, as that center barrier goes up, the physical state is equally likely to be found in the left well or the right well, forming those 2 sharp peaks. Now things get really interesting when we look at the bottom row. Here, a bias of 0.7 has been applied. We've literally tilted the energy landscape. In that bottom left graph, the well on the right side is now sitting at a lower energy state than the one on the left. And consequently, if you check out the bottom right probability graph, that purple peak on the right is much higher. The natural physics of the system is effortlessly sampling this data. By just tweaking these physical barriers and tilts, we can program the probability distribution directly, entirely bypassing the need for crude, energy-intensive digital simulations.
And the sheer efficiency of these physical transitions is just fascinating. These histograms show the distribution of work, essentially the energy cost, required to couple these physical oscillators together. On the left side, we have the work distribution for 2 coupled Gaussian potentials, and on the right, we have a Gaussian coupled to a double well. Those blue bars you're seeing, they represent the probability of different work values occurring during the physical process. But I want you to look really closely at the vertical dashed line in both of those graphs. That represents the mean expected work. It's hovering right around 4 to 5 kBt. Now remember that Landauer limit we talked about earlier? The theoretical absolute minimum? That's roughly 0.7 kBt. This means this physical process is operating at absolute peak thermodynamic efficiency. It is functioning at energy levels that are many orders of magnitude lower than what a standard digital transistor requires to do the exact same probabilistic math.
So, let's look at Section 3,
Energy-based models, applying physics to AI.
To prove that this isn't just a bunch of theoretical physics, researchers actually mapped these dynamics to a probabilistic graphical model. What we are looking at here is a three-dimensional Gaussian model. The three panels show different 2D slices of this 3D data, x0 versus x1, x0 versus x2, and x1 versus x2. The blue dots represent the true training data. The orange dots, however, are the samples generated directly by the thermodynamic model. Just look at how perfectly those orange samples overlap and map right onto the blue data points. It's incredible. This perfectly illustrates how thermodynamic hardware can naturally sample and generate complex correlated data distributions simply by letting the physical hardware settle into its natural energy states.
And to prove this actually scales to real-world machine learning tasks, here we have a Gaussian mixture model trained on the famous MNSD dataset of handwritten digits. What you are looking at on screen are the 20 individual Gaussian components, or clusters, of the model. The numbers floating above each image represent the mixing probability, which is essentially how much weight that specific cluster carries in the model. Because the thermodynamic hardware naturally seeks out the optimal energy states to represent the data it's being fed, each of these clusters organically settles into the physical shape of different handwritten digits. You can clearly see the 3s, the 8s, the 9s, and so on. The hardware is physically learning the distribution of human handwriting.
So the absolutely crucial takeaway here is that these elemental thermodynamic potentials are essentially building blocks. They can be combined to build highly complex, highly expressive models. We just saw Gaussian mixture models, but this totally extends to hidden Markov models for analyzing sequential data, continuous Ising models for modeling magnetic spins, and even what researchers are calling thermoformers. Thermoformers are literal thermodynamic hardware versions of the transformer architectures that power today's massive large language models, but they operate at a fraction of the energy cost. It's a real game changer.
All right, Section 4, Thermodynamic Neurons. Let's take all this from theory to actual hardware.
This is the real deal right here. You are looking at an optical image of a macroscopic layout of an analog thermodynamic computer chip. It is physically made of superconducting aluminum deposited straight onto a silicon wafer. See that snaking, winding path right in the center? That is a coplanar waveguide. And notice those lines coming in from the top left and the bottom left? Those are dedicated flux lines. By sending very precise direct current pulses through these lines, engineers can exactly tune the magnetic flux. And doing that physically alters the tilt and the barrier of the energy landscape we were talking about earlier, and it does it in real time.
Now, if we zoom in with a scanning electron microscope, we arrive at the absolute heart of the thermodynamic neuron. This is the DC squid, and it's located right at the open end of that waveguide we just looked at. SQUID stands for Superconducting Quantum Interference Device. Do you see those overlapping rectangular shapes in the image? Those contain Josephson junctions, which essentially act as quantum barriers. In this specific circuit, the SQUID acts as a highly tunable nonlinear inductor. This microscopic piece of engineering right here is what physically realizes the adjustable double-well potentials we saw in the graphs earlier.
Let's move over to the circuit schematics to see how this all builds into a functional working device. On the left side, we see the coplanar waveguide segment, which is represented as an elongated transmission line. Functionally, as you can see shown on the right side of the slide, this entire setup acts as a parallel LC circuit. That means it has an equivalent inductance, which is represented by that squiggly coil, and a capacitance represented by the parallel lines. That circle with the two X marks inside it, that represents the DC squid along with its Josephson junctions. The curved arrows show exactly how the external flux lines couple into the main circuit to control it. Now, because this entire thing uses superconducting materials, it operates with virtually zero dissipation. The only noise in the system is the ambient thermal heat, which is exactly what drives the computation. And here we have the experimental data proving that the hardware actually works exactly as the physics demands it should. In graph A on the left, we see this beautiful sigmoidal relationship. The y-axis shows the probability of the state being in one of the specific wells, and the x-axis represents the magnetic flux tilt we apply to it. As we physically tilt the potential, the probability smoothly flips from 1 down to 0, forming a perfect S-curve. Those dots you see are the real actual hardware measurements, and they're perfectly tracking along the theoretical solid lines. Now take a look at graph B on the right. This plots the width of that S-curve against the temperature. As the physical temperature of the chip increases, the width parameter grows right along with it. This directly validates that ambient heat, that thermal fluctuation we've been talking about, is actively interacting with the barrier escape energy. It proves definitively that we can use ambient heat as a highly controllable computational resource.
Which brings us to our final section, Section 5,
the future of computing, surfing the noise.
We are basically on a collision course with physics right now. Step 1. As we shrink our digital transistors down to the atomic scale just to try and keep up with Moore's law, quantum effects naturally begin to disrupt the strict determinism of binary logic. We literally cannot build classical chips much smaller than we already are. Step 2. This creates a massive digital energy bottleneck as we are essentially forced to build entire power plants just to brute force AI training on highly inefficient hardware. Step 3. This makes the transition to highly efficient continuous variable thermodynamic chips not just a fun little science project, but an absolute necessity for the sustainable scaling of artificial intelligence.
And that leaves us with a truly provocative thought to end on today. If thermodynamic computing scales up the way it's promised to, the truly intelligent systems of tomorrow won't require us to build dedicated nuclear reactors just to keep them running. Instead of constantly fighting the environment, the AI of the future might just surf the natural thermodynamic noise that's already all around us, computing at the very limits of what the laws of physics will allow. Thanks for joining us for this explainer. We'll see you next time.